potential. What about 2? Rank the following according to ease of oxidation. We're going to go for the, depending on how you want to phrase that, the biggest negative, okay, or the most negative number is going to be the easiest to oxidize. Why? We're looking at a reduction potential. Okay, if we want to look at the oxidation, what do we have to do? Change the sign on all of them. So the most negative will become the most positive oxidation potential. So it looks like it would be aluminum, nickel, and hydrogen. Okay? Good? Everyone getting these okay? Last one, just to be tricky, rank the following according to reducing strength. What are we looking at there? What happened to the species? It was oxidized. How do we know it was oxidized? Because that ing, it's causing something else to be reduced, which means it needs to be oxidized. So we would go through and take a look at those species and rank them according to which one would be easiest to be oxidized. That would be our correct sequence. Okay? Did check that, and hopefully those answers match up. Questions about that? Yes?
So just because the reduction has an ing at the end means...
That makes it an agent, an oxidizing or reducing agent. Agents act or do whatever their name says on something else. That definitely should have been way earlier. We can go back to our water analogy. Which one's going to hurt when it falls, red or blue? Which one hurts more, red or blue? Red, why? Okay. What did you assume? You assumed that you were standing at the bottom. What if you're not standing at the bottom? Okay. Depending on where we decide to stand, we may end up seeing different effects for what these overall things are referring to. So what we've got to do is come up with a standard. Okay, where are we detecting these things? And to be consistent, we have to make sure that our standard is the same across the board. Okay? What standard do we typically use and what we will use for the rest of the semester? Anybody know? We're going to, oh, come on. Thought it was right there. We're going to use hydrogen. How do we know we use hydrogen? Go back to your reduction potential. Where's our 0 mark? That's our hydrogen. Okay? So we decided a long time ago that that's going to be our 0 mark for our individual values. Everything else is going to be ranked based off of hydrogen. Okay? So, what exactly are we trying to measure in each of these cases? Looking at the flow of electrons. Okay? So it's ultimately volts. So what we could try and do is look at the actual electron motion. But if we evaluate the energy stored by a single electron, it gets to be a really, really small number. Okay? So someone went through and actually decided to scale a little bit differently. And that's where we looked at our hydrogen. So that's where we get our cell potential, our 0 for our hydrogen. We can look at the electron flow associated there and set that as our 0 value. I thought this was talking about something else, but it's not quite yet. We'll get there in a second. So some conclusions that we can pull from reduction potentials. The more positive our reduction potential, the more likely it is to be reduced. Okay? And since everything we're dealing with is a reduction potential, or everything that we look at is provided as a reduction potential, that's going to be helpful to analyze. Okay? That means it's the more readily it will act as an oxidizing agent. Okay, why? The easier it is to reduce, okay, the more likely it's going to take electrons from something else or cause something else to be oxidized. So it's a really good oxidizing agent. Okay? This also implies a necessarily more negative oxidation potential. Okay, so the more positive your reduction, when we change the sign and look at the oxidation, becomes a more negative oxidation potential. Okay? We could go through and look at the negative reduction potentials, And we would expect that that conjugate, so the one on the product side, would be more likely to be oxidized. Okay, why? Because if we flip that equation, we're now looking at a very positive oxidation potential. Okay? This can apply back to it acting as a really good reducing agent because it can cause something else to be reduced. Because it's willing to give up those electrons to force something else to change its oxidation state. Okay? Yeah, let's go ahead and look at this. Determine if the following reactions will produce a measurable EMF. Okay? What does measurable EMF need to be? It needs to have a positive cell potential. Okay? And then determine which of the following would produce the highest voltage. Okay? And then as a very last question, how could you change the reactions to produce a measurable EMF? So if one of those does not generate a positive or spontaneous reaction, what can we do to change that situation such that we can make it positive? To solve these, what would you need? We need the reduction potential tables, so there we go. Okay, I'll let you free rein at this again, see what you guys can come up with. Second one is positive. Any of the others? Third one's positive. How can we make the first one positive? Run the reaction the other direction, so flip the reaction. Between the second and the third, which one generates the highest voltage? Actually, don't even remember. Third one, so I believe we got the numbers down at the bottom. You'll notice that last one. Okay, I believe if you added these up slightly incorrectly, the first two should have been straightforward. The second two, you might not have gotten those numbers. Okay, why would your numbers be different? Probably looked at the coefficients. Do the coefficients affect the cell potential? Turns out not. The cell potential does not change if we run the reaction multiple times. We get the exact same cell potential. Which is kind of a tricky thing. Why would it not change? Okay, well, first off, before we do that, any questions about what's up there other than the cell potential not changing? Okay. So when we go through and look at these, okay, when we looked at enthalpy, if we went through and multiplied by 2, what happened? We ran that reaction twice, so if we had a negative delta H, what does that mean? The reaction was exothermic and heat was released, so it would be a product. If we go through and double this reaction, we run it twice, do we get more heat? Yeah. We end up breaking and making more bonds, we generate more heat. If we go through and look at a cell potential, what happens when we double it? Okay, if I go through and multiply the coefficients, 2, 2, and 2, the cell potential doesn't change. Oh, man. I thought you guys were going to remind me about that. Our cell potential ends up not changing, and the question becomes why. Okay, well, enthalpy is a form of energy. If we look at our cell potential, we have to see how it's related back to energy. It was an energy per charge of electron. Okay? So if we go through and evaluate our cell potential, okay, if we look at just the units on it, our volts was what? Why does this look really weird? This is equal to, that's not showing up. What the heck is going on? This is equal to 0.16. What were our other units? Joules per coulomb. Okay? Where coulomb was effectively the charge on an electron. If we go through and look at this, yes, we would expect more energy if we run the reaction twice. We might expect twice the energy. what happens to the amount of electrons? If we run the reaction twice, what happens to the coefficient in front of our electrons? Also doubles. So yes, we get twice the amount of energy, but we also get twice the amount of charge. Those two are related inversely. So if I double the energy and double the charge, what's the net result to my cell potential? No change. Okay? Where is this coming from? This comes back to looking at Faraday, and he came up with a relationship between the work that you could feasibly pull out of a cell reaction or a galvanic cell, and he related that back to the cell potential, the moles of electrons transferred, and a constant known as Faraday's constant. Okay? So what he's referring to is if we look at our work for an individual reaction, if we go through and double our reaction, we could expect more energy coming out of it. But at the same time, we end up changing our other values. Okay? So if we looked for solving for our energy for our cell potential equals our work over NF, put in that little negative there. If our work doubles by doubling the reaction, we also double the number of moles of electrons. Our net result is no change. So our cell potential does not change when we double the reaction, okay? Or triple the reaction, or any multiple thereof. Okay? The other big constant that comes out of that is Faraday's constant, 96,485 joules per volt per mole. Okay? And our cell potential is still E. Okay? So if we went back to that previous problem, when we had to double the coefficients, our cell potential doesn't change, which is why we get the smaller, or actually I don't know what size difference the numbers were. Okay? Kind of makes sense? So your cell potential does increase in energy, but it also increases in moles of electrons. Those effects cancel out, which then means your cell potential doesn't change. Okay? We have seen this work show up before. Okay? Work was something that we saw in the thermodynamics chapter. We could relate that back to our free energy. Okay? So we can now tie the energy of a cell reaction back to the energy of Gibbs, where Gibbs was supposed to represent the energy of everything. Okay? What we can end up solving for or determining is that delta G for an individual cell potential reaction will equal negative the moles of electrons transferred in the course of that reaction times Faraday's constant times the cell potential for that reaction. Okay? You should already be kind of scared about this, because what does that mean? You remember all of those reactions, or all the equations that we used in the thermodynamics chapter? We looked at how Q and K and R and T and all of that affect Gibbs free energy. We can now tie those all back to our cell potentials. Okay? Because up to this point, we've been looking at a reaction that is a spontaneous reaction that had nothing to do with delta G. We're using all sorts of other new funky units. There is a relationship between them. That's where this ties in. Okay? So it's kind of cool as far as the parallels go. If we go back to spontaneous versus non-spontaneous, a negative delta G was a spontaneous reaction. When we look at our cell potentials, we said our cell potentials needed to be positive. How can we match those two theories to each other? We have to incorporate that negative sign. Okay? Which is where I was talking about earlier. That's what that negative is doing. Okay? We took two individual theories, our thermodynamics theory and our cell potential theory. Our cell potential theory, we decided we wanted to be positive. To make that mesh with our Gibbs free energy, in the course of putting that equation together, we have to incorporate that negative sign. Okay? At standard conditions, we get a very similar question, or a very similar equation. We just get delta G naught equals NFE, or NFE naught. Okay? Questions about those relationships? Okay, so I want you to go through and do some more work with this, because in theory you guys already know your thermodynamics, so you should be able to correlate these things to each other. I want to know the equilibrium constant for the reaction of iron solid with sufficient oxygen when submerged in water. We have to add all that fun stuff at standard conditions. Okay? On an exam, I would provide you those equations. Okay? I would. Okay? So we've got the reduction equations, the reduction potentials. What should our cell potential be, positive or negative? How do we want to put it together? If we're going to try and get the equilibrium constant, we want the spontaneous reaction, which means our cell potential needs to be added in such a way that we get a positive number. Okay? Go through and kind of piece it together and see what you can get. So what we could go through and do to correlate all of these individual things is to get K, we'd have to know delta G naught. To know delta G naught, we have to know our cell potential. To know our cell potential, we have to add our two equations together to generate that positive cell potential. So we could go back through, notice that to get the positive cell potential, we'd have to flip our iron equation. We could go through and say, yes, that's what we had to do to get a positive value. The other way we could do it, why do we know we have to flip the iron? The equation says iron solid reacts with oxygen. If we didn't flip that equation, does iron solid on the same side as our oxygen? No. Okay? So we'd flip it. Okay? Our overall equation is not allowed to have electrons in it. Okay? So we have to make sure that we can account for that when we balance our reaction. How do we fix that? Our iron had 2 electrons. Our oxygen required 4 electrons. What do we have to do? We'll multiply our iron equation by 2 to go through and change our coefficients around so that when we balance our overall reaction, our electrons cancel out on both sides of the equation. Yes? What happens to the cell potential? Stays the same. We may be running the reaction and generating more energy, but we're also increasing the number of electrons. They counteract each other. Our cell potential stays the same, just positive sign because we flipped the equation. We can add those two up. We now get our cell potential for the reaction. So our reaction cell potential in this case, should have put in a positive there, is 0.84 volts. How is cell potential related to Gibbs free energy? We've got an equation there that correlates those two. So we can do our substitution. The tricky part on that one is, what is N? N is the number of electron moles transferred in the course of the reaction. How many electrons were produced when we did our iron oxidation? 4. Those 4 electrons were immediately consumed by our oxygen. How many electrons were necessary to balance this reaction? 4. What's our N value in our Faraday's our relationship? 4 moles of electrons times Faraday's constant, which is the energy per mole Kelvin. And we can multiply by our volts. When we go through and do that, we'll get our delta G naught. And we now have the Gibbs free energy for that reaction in units of joules. First, did I leave the negative off? Yep, thank you. What's that? It's mole of electrons. The charge on electrons are negative. Yeah, if you go back to the equation, delta G equals negative. Okay. That gives us our Gibbs free energy. Once we have the Gibbs free energy at standard conditions, we can then plug that back into our expression that relates free energy to K, to our equilibrium constant. We can now plug that in and solve. I got a couple questions on what value you should use for R. 8.3145 is the correct number sequence. You might end up using 0.0083145. Why would you use that one? because you converted your Gibbs free energy into kilojoules. Okay? We have to make sure that the units cancel. So use whatever R is necessary to cause the units to cancel. Okay? I decided to use the 8.3145 because when I went through and solved for my Gibbs free energy, what's my unit? Joules. Okay? Make sure you watch out for that. That shows up in your thermochemistry chapter as well. You've got to make sure those units cancel out. Okay? So we could go through and solve this stepwise like we just went through and did. Do you have any questions on that? Yes. No. The cell potential does not change with the coefficients. That is always for cell potentials. So when you do Hess's law, you're looking at enthalpy or Gibbs free energy, then it changes. Okay? It doesn't change with the cell potential because you're also increasing the number of electrons. The electrons and the energy cancel each other out. Sorry. Are there other questions on that now that I deleted everything? Oh, good. Look at that. Okay, so what we could go through and do is instead of solving each of these stepwise, is go through and kind of relate the two equations. So from thermodynamics, we can summarize down to our delta G naught at equilibrium gives us negative RT ln of K. Okay, and the things that we need to solve for that is that at equilibrium, our Q becomes K, and our delta G equals 0. We could go through and tie this back to our electrochemistry, and we can apply our standard conditions, and depending on how we want to work on this, we could come up with two possible conclusions. We can either solve for our equilibrium constant, given the cell potential information, as shown in blue, or we could go through and solve for our cell potential at equilibrium, as we've got shown in red. Okay, so it really just depends how you want to solve those expressions. All we're doing is tying those two things together. We did exactly this when we did that last problem. Okay, so it's just a question of how far into it you want to get. Do you want to solve each of the individual steps of the equation, or do you want to just plug into one equation and hope what you plugged in was correct? Okay, because I did already mess up the negative sign. Actually, it looks like I did that right. Looks like we've got that set up okay. Okay? So what this stepwise goes through and does, the exact same thing that we just did in the last problem. We just jump to pretty much the final step. Okay? Get it? The Nernst step? Like the next step? Nernst. It's classy. I know. Okay? What we're looking at with the Nernst equation is we're now going to tie in our cell potentials back to equilibrium, or not equilibrium, our unequilibrium unconstant, our Q value. So we can now calculate the cell potential at non-standard conditions for any reaction, or for any redox reaction. So all we've gone through and done is doing some more substitution to generate that expression. I'm pretty sure your homework goes through some of these. You will be expected to solve one problem like this on the exam. After the exam, we'll talk about a trickier application of this, where we're really getting into concentration cells and ultimately pH meters. So we can look at a brief, I think I've got a brief example here. No, I decided to not do a brief example of that. So when you go through and work with these, Q is equal to what? How do you solve for Q? It's your products over your reactants. Make sure that you watch out for what? Let's say this was your equation. I don't know why I said D there. If we were going to write out our Q, it would be the concentration of C to the C power. You have to watch out for those expressions. It's going to come from your balanced equation. Okay. So given this, you should be able to solve, I'm pretty sure I went through and removed any more advanced questions with the Nernst equation. You should be able to solve all your homework problems as far as this goes. Okay? So you have to remember equilibrium expressions, what they are, what they mean, how to apply them. Okay? And we will make that much trickier after the exam. The last thing, yes, sorry.
I have a question about the passing. Like, what
Yep.
kind of question do we get when we use that?
What is the cell potential for the reaction where the concentration of, I need an equation. Just give me an equation. Let's say we're looking at, what was the, this one's correct, isn't it? To copper metal plus zinc ion. What is the cell potential for this reaction, giving the starting concentration of copper ion, or the concentrations of your copper ion is, let's say, 0.1 molar, and the concentration of zinc ion is 0.2 molar. All right. What you would be able to do is calculate the standard cell potential by doing what? You look up your reduction cell potentials. Okay, your table of reduction potentials at standard conditions. Okay. Just to be tricky, let's be obnoxious. Let's say those concentrations and at a temperature of, oh, I don't know, 23 degrees Kelvin. Make it nice and cold. That reaction, or our cell potential that we're going to get out of that, is going to be different from our standard conditions because we're not at standard conditions. How is it differ? That's this term. So we would go through and substitute in our R value. The R value we should use should be our 8.3145. Temperature would be Kelvin, our 23 Kelvin. N would be moles of electrons, which in this case, see how many of you remember that equation? 2 moles of electrons for that equation. How do you know 2? Break it into your half reactions and look at how many electrons are transferred. It should come out to be 2. Faraday's constant, you know. Q. What is Q going to be in this case for this problem? What are your products? Zinc ion times copper solid. Should copper solid show up in it? Why not? It's a solid. We won't worry about it. Okay? That gives us our Q. We can plug in the numbers and solve. Okay? What? Works for pressures as well. Okay? Questions about that?
How does it affect when your temperature is 22 Kelvin, but then you're getting your Ecell as standard?
So just like with our Gibbs free energy, our standard cell potential is always going to be at 298. What's the cell potential at 23 Kelvin? It's going to be whatever our standard cell potential is with some extra term shifting us off of that. That's where our temperature condition comes into play. So that's where our variation comes from. Does that make sense? Good job. You just lost one topic from the exam. Okay? Any more questions on that, since that is where we'll stop? I won't push it any further with that. We will not worry about corrosion. So the one topic, let me slip through some of this here. The next section was just going to be corrosion. I would expect that you guys should be able to piece it together, but we won't directly test on any of that. So these next few slides go through a whole bunch of different examples looking at corrosion and how you can prevent corrosion. Come on. This is the slide I wanted to get to. So corrosion is not going to be on exam 3. Add that topic here. That's not how you spell corrosion, is it? Is it? That looks right. Don't tell me I'm wrong. So corrosion won't show up on exam 3. Concentration cells, the tricky concentration cells won't show up on exam 3, which is kind of an odd thing to say. Nernst is there. We'll only look at one example of that, just like what we just talked about. I just gave you an example of something that would work for a concentration, sort of concentration cell question. We won't have any questions on batteries. You never would, because I can't come up with a question that's not just strict memorization. And then electrolysis is definitely not going to be on the exam either. Okay? We will finish up these slides after the exam and then start into the next chapter. So realize that you will still be responsible for this material, but on the final exam, not on exam 3. Okay? If you've got questions, feel free to talk to me. Sorry about running a little bit late there. Come on, stop.